problem 3, I'll say I felt is more standard. Yeah. So this is marbles. So Bessie and Elsie are playing a game of marbles. And Elsie, yeah. So Bessie holds out A marbles and Elsie has to guess if it's even or odd. And if Elsie is correct, she wins the A marbles from Bessie. And if she guesses incorrectly, then she loses A marbles. Yeah. And basically Elsie wants to have Elsie keeps announcing even and odd and wants to make the lexicographically smallest sequence such that no matter what Bessie does, Elsie will still win. Yeah, this is problem 3. I believe someone else will be presenting too. Yeah. Um, yeah, so this is asking to find a lexicographically minimum turn sequence so that Elsie will not lose regardless, no matter what. And yeah, basically Elsie can Elsie can see Elsie knows for each turn what the K Elsie knows for each turn what marbles Bessie might pick, right? Yeah. So so I guess here there's Elsie has 10 marbles and there's 3 turns. Yeah, and then Bessie can make 2 potential moves. Yeah. These are the potential moves Bessie can make in each turn. So the optimal answer is even, odd. I guess if you pick even, then Bessie will pick the worst case, which is odd. And then if you pick even, then Bessie will pick worst case, which is odd. So Elsie will lose 2 marbles. And then at the end, Elsie can just pick odd, right? Yeah, so I'll explain about problem 1 later if we have more time. But let's yeah, let's yeah. Yeah, I'll answer questions about problem 1 later if there's more time, but let's go over the idea for problem 3. So let me go back to the OneNote. Yeah, so in the ideal case, since we want lexicographically smallest, then Elsie can just keep guessing even, since that's like the lexicographically smallest string you can make, right? So there's M turns, right? So basically, let's so let's do the following kind of strategy. So wishfully you want to keep guessing even. So let's say you guess even. You're only allowed to guess even if you know for sure that you want there's a way to not lose no matter what Bessie does. So basically if I so I can guess even if I know that in the next turn, I'm going to lose no matter what. I'm going to win no matter what. So let's consider how we can check if we're going to win no matter what. So let's say I have K marbles left. So basically the optimal kind of play, if I want to maximize my number of marbles, which will tell me whether or not to pick even, I should pick even. I should pick even if after I picked even, the number of marbles cannot drop less than or equal to 0, right? So basically, let's think about what's the optimal strategy. So if Bessie's um so if all of them are like even, like let's say K equals 3, right? And then all of them are even, like 2, 4, 8. Then you can maximize your marbles by guessing even. And if all of them are odd, like let's say, so if you guess even, then Bessie, if they pick the worst case, then you'll gain 2 marbles. And if all of them are odd, then yeah, then you can just pick odd, and in the worst case you'll get 1. And the other case is where you have even and odd elements, right? 7 and then 4. So if you pick even, then Bessie will pick this odd number and you lose 7. And if you pick odd, then Bessie will pick uh, the largest even number and you'll get -4. So it's optimal to pick odd. So basically, for you consider like if you have things with different parity, you consider, so if you have things with different parity, so if you have even things and odd things, then you consider the largest number and you pick the opposite parity. So in this case, the largest number is 7. So if you want to maximize your chance, like if you want to win and minimize your losses, then it's better to pick, oh, sorry, I flipped it around. It's better to pick even. Yeah, it's better to guess. Wait, no, I was correct. Yeah, it's better to pick odd, um, because you'll only lose 4 in the worst case. If you pick even, then you'll lose 7 in the worst case. Yeah. So this is kind of the optimal strategy. So basically now we have like an O of n squared way. It's too slow to pass everything, but this is O of n squared idea. So the idea is play even whenever you can, when it's possible, uh, when uh, you can win. Otherwise pick odd. Like you play even when you can, and if you check whether you can win the rest of the game, so you have K marbles left, then you play the game optimally. By if everything's even, pick even, and if everything's odd, pick odd, and then if there's 2 different parities, then just pick the one that minimizes your losses. Then you initially have K marbles, and your score over time might fluctuate something like this. And you basically win if it's always greater than 0, right? So you win if the score is always greater than 0, no matter what Bessie does. But this is too slow. But what we can do is we can speed up this checking if we can win the game with K marbles. Um, Essentially, we want to find the minimum prefix sum. And right, so if like first you might have a loss of +4, you have a gain of like 10, and then -20 or something. Basically the minimum prefix sum will tell you whether the game will be lost. So you basically win if k is, or min prefix sum um, is strictly greater than -k, right? So if you lose more than k, then if you lose at least k, then you're going to lose. So basically, we can do like a dynamic programming. So it's basically a DPI is like min prefix sum of games. Yeah. So yeah, so DPI is the min prefix sum of gains when playing optimally, like using the strategy to like lose the least or gain the most. Yeah. So this we can compute DPI, right? Because the first case is you play even, and then the second case is you play odd. So yeah, if you play even, you'll get some gain of like XE, and then if you play odd, you'll get some gain of XO. So yeah, uh, yeah. So yeah, you'll have like DPI. Um, yeah. Uh, so XE, or basically your delta, it could be negative or it could be positive. Um, um, maybe it could be zero. I'd have to think, but it's basically the minimum. It's like the minimum prefix sum. So it's gonna be min of um like whatever you gain, and um and then I guess in the beginning you also have prefix sum of zero, and then x plus dp I plus one, right? Yeah, so that's how you compute the minimum prefix sum, just because when you're making your ith turn, then you have like some gains and losses from the I plus one's turn, and the minimum prefix sum from the I plus one's turn translates to x plus the minimum prefix sum, because there's this x here. And then there's a possibility that the minimum prefix sum is actually attained in the very beginning, right? Or maybe the minimum prefix sum is attained after you get the first move. So you'll have this kind of transition. DPI is min x0 and x plus DPI plus 1. Yeah, so the strategy should be like play even when you can win the rest of the game. Otherwise pick odd. And now we have a very easy way to see if we can win the rest of the game. So let's say we pick E at time step I, then we have some kind of score S, right? And then, or I guess, yeah, we have K marbles left after we play E. Then we can win the game as long as DP I plus one is is strictly greater than negative K. So if it's strictly greater than negative K, then it's still possible to win the game. So we want to pick even. Um, Otherwise, we should pick odd. Summarize this. So for many of these problems where you want to find something that's lexicographically minimum, we have even is less than odd. So it's always good to be able to pick even. It's always better to pick even if you have a choice between even and odd and both are valid. Yeah, so basically the idea is you try to pick even as long as it's possible to win the rest of the game. And if you can't pick even, then you can pick odd. And to check if it's possible to win the rest of the game, um, uh, you have to check given the optimal play strategy, whether um whether the like the total number of yeah whether the total number of marbles is strictly greater than zero the whole time. And this is basically looking at the min prefix sum of gains, and you can compute this using a DP. It's like a suffix DP. And if you have K marbles after playing a turn, then you're going to win as long as DPI plus 1 is greater than negative K. So yeah, computing the DP and then deciding between even and odd, this will be O of N. Yeah, any questions? Um, yeah, um, I guess I'm done with problem 3, but yeah. Can you summarize? Yeah, sure. Yeah, I can summarize the solution ideal. So this is question 3. Um, yeah, so you want to find the lexicographically smallest sequence so that you can still win. And the idea is like you can build the solution answer one by one, and it's always optimal to pick even over odd, because that's just like that will just make your thing lexicographically smaller. So we want to check if it's valid to pick even. And yeah, there's an optimal strategy. We pick even if it's possible to win the rest of the game without having zero marbles. And you always, if you know the parity of what Bessie has, so if you know Bessie always has even, then it's better to guess even. And if you know Bessie always has odd, then it's better to guess odd. And otherwise, if Bessie has a choice, then you pick which one will uh will su suffer the least losses. Yeah. So in this case, it's better to pick odd. And you want your minimum prefix sum. So basically, your losses will be like some kind of ups and downs, and um, you want your minimum prefix sum to be high enough so that this never hits 0 from k, and you can compute that using a suffix dp, which is the minimum prefix sum of gains when you're playing optimally. Yeah. So this is like an O of 1 dynamic program. And when you're picking even, yeah, you can just look at your DP to check whether it's still possible to win after picking even. And if you can't pick even, then you should pick odd. Yeah, yeah. Wait. Max, I think you're next. Problem 2. Oh,